Hello, I'm Michael from engineering at the University of Waikato. I'm working with a psychologist on an interesting problem implementing some processing that goes on in the human visual system into computers and therefore intended for robotic autonomous control. It brings up some interesting issues. I'll start back here using convolutional neural networks for image classification and for object detection. And you'll see here a representation of one convolutional neural network, the VGG1, which you can see is layers of convolutions, which make sense. Even in computer vision, convolutions were used for match filtering to identify patterns, but also that by using spatially invariant operators, we greatly reduce the number of parameters that have to be learned in the network. Here goes an interesting problem with tests of convolutional neural networks on object classification. On the left is showing a cat, and this is from some work done by Geros and others back in 2019. So you've got a cat on the left, but what if we change the texture of the cat? In the middle image is the texture of an elephant skin, and on the right is the cat substituted with the elephant skin. Now, if you ask a convolutional neural network to classify that, it will get the cat on the left correct, 70% or so for the tabby cat. It gets the skin of the elephant correct, but it says the cat on the right that looks strange is an Indian elephant. But if you ask a human the same problem, they will mostly say it's a cat. It's a strange looking cat, but it's definitely a cat. And so there's something different that humans are doing when they recognise objects than what these deep learning convolutional neural networks are learning up. The people who published this paper went on to show that they demonstrated essentially that if you used a local texture classification and a bag of words approach, you could actually do almost as well as a convolutional neural network on the ImageNet training set. And they were suggesting that, in fact, is the solution that these convolutional neural networks are finding. So we've got evidence that they're not doing what humans do in the brain. The interesting thing is, well, we don't know exactly how the brain works on object detection, but we do know how the brain works on detecting motion from the camera, from your view of your eye. So if you close one eye, just with monocular vision, you can navigate all the way around the room. You won't collide into people, you won't hit things, you know how you're moving. And we can do that from vision alone. We understand the process, years of psychological tests and observing neurons in primate brains. I've got a bit of a picture here. We know in the V1 neurons that there are spatial temporal filters that are bandwidth and direction tuned to detecting edges moving at different speeds and in different directions. And in the MT, the medial temporal, they are then speed tuned, leading to, in the MST region of the brain, neurons that fire at the rate at which objects move through the brain, and from that the brain can work out how you're moving in the world. Here goes a picture of how that speed tuning works. Basically, the filters are temporal frequency and spatial frequency. Think of say, a video stream which has two spatial dimensions and a time dimension, and we do a 3D Fourier transform of it to get to both spatial and temporal frequencies. The interesting thing, a moving object in the field lands on a line in the Fourier space of which the orientation of the line is related to the speed of which it's travelled. And we know the neurons in the human brain are tuned to that. Here goes some work we've been doing. We've implemented this in computer. There is a scene here. The camera moved into the scene. Unfortunately, I couldn't get a video going in this to show the motion, but the camera's just moving into the scene, and we can get out here's the optic flow. That can be done other ways in computer vision, but we know there are problems the way that computer vision algorithms do it, of which humans don't have those problems. So the question I would pose to you in the last 8 seconds is, what if we tried to train up our deep learning techniques to do this problem. And the question I raised, which I think is going to be interesting research, and I wish I'd started but ran out of time, is does the convolutional neural network generate filters and pattern filters, etc., same as what we know are already happening in the human brain? So that's the question I would like to investigate, and it looks like I'm on negative time now, so I better stop there.